Welcome, everyone. Great to see you. My name's Erik Blaser. I'm looking forward to meeting with you all at some point throughout the day. So I'm part of the Early Minds Lab also. My background, though, is in more like visual psychophysics. That's where I got my start. So I'm within the Early Minds Lab, we're all collaborating to some extent, at least in our joint meetings, bouncing ideas off of one another. But most of my work lately has been done in collaboration with Dr. Caldi. Um, I just wanted to quick go through a couple projects that would be just to give you a flavor of the kind of different approaches that I'm using and questions that I'm curious about and our team is curious about. This work here on the left on temporal processing was done with Julie Freschel, who went on to a career in industry. And Bill Liang here, this work on scene processing, he is working on his postdoc in Germany right now. Um, so the kinds of the general area where we've been interested is like what you might call like middle level vision, so not like super early level like V1 cells kind of stuff, and not yet like face processing or reading or something like this. But this kind of mid-level pattern processing, layout, scene, 3D construction kind of stuff. This work on the left here was yes, left, was interested in temporal processing. So just as you need to parse up the visual scene into coherent objects and shapes and find spatial boundaries, you also need to find temporal boundaries. When did one event start or stop? When do I stop the processing on a particular object and decide what it is or something along that nature? So we tailored these kind of clever displays that have that leverage visual search. So the adult, if we're instructing an adult or even an infant, is finding a pop-out target here. So one item that's the oddball out in this cluttered background of other little shapes. Um, this is a temporal display, so they're flickering rapidly at the person. There are two targets that are competing for the observer's attention. One of them you'll be more likely to see if you have like a fast temporal processing brain, and one you'll be more likely to see if you have a slower pace. You can think of it like a window in which you integrate information. If the window is very short, you're more likely to see that fast target, and or otherwise you will miss it and integrate over it. But in exchange, you get to see that target that is only present for you if you're integrating over a longer period. Neither answer is right or wrong. It's just a difference in kind of tuning. But it is something that you can look at developmentally and see this trajectory toward actually slower processing in infancy toward faster temporal processing in adulthood. We also did a comparison between typically developing toddlers and toddlers who were diagnosed at 2 years old with autism spectrum disorder, who have shorter temporal windows for the same age-matched controls. So that's that work. We've published on these different age groups, and the last work to come out of that was work on infants that were currently in revisions. Over here, Bill was interested in scene processing, basically. So here we're leveraging visual search again. These are infants. We also had an adult version, but the infants are more fun to think about. They're looking for a particular target in this scene. We let them know what they're looking for because it's a tiny little tablet, there it is, or a little computer screen, but they may not know what that is, but at some point, some Teletubbies video is going to play really small in there. So after they realize that, after a couple trials, the kid will, we suppose, will start to gravitate their eye movements toward there. So if it wasn't obvious already, we're using eye tracking and pupillometry as part of the measures that we're doing. So here we're basically looking for how quickly they can find that target. That's fine. But what we're looking for here is what's called contextual cueing, like at least an implicit building of a structural, in this case, because of this three-dimensional layout representation of the scene that can aid you as the trials go on, even if you're looking at this room from different viewpoints, which we manipulated. Those infants and adults will be more readily able to find that target as they build that representation. Like, oh, it's to the left of the bed, and you go right there, even if you're looking from a different view. Um, and this was some fun stuff. This was actually just an adult study. This was some work on scene memory. Had a undergraduate honor student strapped a GoPro camera to his chest, and he walked around parks around in Boston and took these videos that we sliced up into individual scenes. We would show participants a scene. This was an online study, the first one that I participated in. Show an individual a scene, and then take it away real quick, 500 milliseconds, and then give them like a scroll wheel where they could like rapidly rewalk that walk in the park and they try to locate where that scene was in that scene wheel. People are quite good at this. And actually, the one thing that was counter, we predicted the opposite. It's a nice moment in science where you predicted one thing and actually find the opposite because that kind of calls your bluff that you weren't like just looking at something really obvious. Um, Here, the counterintuitive thing was that folks were better at finding the scene in those scenes, in those parks that were more self-similar. So when the problem was harder, people got better. So you kind of tune the precision of your memory. You decide to make a more precise coding of a particular scene if you know it's going to be in a more challenging context. So that's it. If we have questions about this stuff, if we're meeting together, we can talk some more or at dinner or reach out by email if anything comes up.